Hello, everyone, and welcome. Today, I would like to talk about permutations. This question provides you an array nums of distinct integers. So those integers are unique. Ask you to return all the possible permutations. So how can we solve this? When you are asked about permutations, think about using recursions and a tree structure to solve this problem. So there's a parent node here, 1, 2, 3, and we choose one of the elements. Let's say we choose element 1. And then we call the function itself to process the remaining elements. So that will be processing 2 and 3. And then we choose, let's say, element 2. And then we call the function again to process the remaining elements. So processing 3. And we have only one element to choose. So after choosing element 3, when we call itself to process remaining, we found there's no remaining elements. So we reach the leaf node and we append this order of element chosen to the results array. And you can also kind of understand the whole process with this depth variable with 0, 1, 2, 3. And this is going through this recursively. Here, I spell out all the possible leaf terminal nodes, and those leaf terminal nodes will be appended together, aggregated as into the result array. And here, I would like to show you how the recursion traverses through all the nodes available and it exhausts all the possibilities. So going start from the parent node 1, 2, 3, and traverse down to depth 1 channel, traverse down to depth 2 channel, then reach leaf terminal node, and then traverse back up to depth 1 channel, traverse down to depth 2 another channel, traverse down to another depth 3 terminal leaf node, and then it goes through this whole process until it finally reach all the possibility exhausted, and so this recursion traversal show you how exactly is happening when you use this technique. And this recursion technique is frequently used in other applications such as games, in artificial intelligence. If you are interested, feel free to Google, for example, the minimax algorithm to research some more details. With all the background introduced, now let's write the code. So first of all, in this permute function, we want to add an argument, the depth, so we can keep track which depth of the node it is, and it initialized to be 0. And in this kind of recursion, we always want to think of ahead of time what happened to the terminal leaf node. So when the length of num equals 0, we know we are at the terminal leaf node. So then we will append the result we'll append our permute to the result array. And so this result array should be accessible for all the codes to this permute function. So we will do a self variable use dot resolve to initialize like this and append. Okay, and then we will think about what it's going to append later, and then it return. Okay, and now let's work from the root node. Okay, so from the root node, we know that if depth is 0, it's a root node, and then we will initialize a tracking device. We call it a tracking device. So just and initialize to be an array with non-elements, but there will be equal number of elements as in the nums array. This is our tracking device. Okay, and then we want to iterate through the nums array. And for each iteration, we want to call our function, the permute function itself, and with the depth plus 1, but we will give it another nums array with one of the element removed. So we create a temp nums array and using this, so it's a copy here, and we remove one of the elements by using the pop method, and the pop method also return what is the element that's popped, and that's helpful for us to keep track. So we'll combine these two as in here. And so, for example, when depth is 0, the element pop will be written into the zeros element in the tracking device. Okay. So, for example, when depth is 0, the element is written to this position, and then we call the permute. So now we have a better idea of what we're going to append here. It will be just the tracking device array when it's completely populated, when it's fully populated. Okay, so that's what we're going to append. And finally, we return to loop now. So if our depth is 0, we know that we have returned to the loop node. And here we simply return the results array. And that concludes our solution here. And let's test this. Submit. And it's done. It's about 28 milliseconds. Finally, we'll analyze for complexity. So it has a time complexity n factorial, and it has a space complexity n factorial to store all the possible permutations. And that's it. I hope you would find this video to be useful. Please feel free to subscribe for more videos, and I'm hoping to see you next time. Goodbye.